Hey, what's going on, guys? Let's see how we can prove this series, whether it is converges or diverges using integral test. But before we do the integral test, we have to know whether it is positive and decreasing, because if it's positive and decreasing, then only we can apply integral test. So let's go ahead and write this as a function and see what happens, right? So here we are going to have 1 over, instead of n I plug x, so this is going to be x, and ln x square plus 4. So this is what we have, and the function is going from 2 to infinity. So if the x is greater than 2, we definitely know it's going to be a positive value, because if you divide any value greater than 2 here, that's going to give us a positive answer. So we know that it's going to be a positive value, and as it approaches infinity, this value becomes bigger, and we know that this whole value is going to be decreasing. So this is positive and decreasing. Therefore, we can go ahead and we can do the integral test. So let's write this one as integral and do the integral test, right? So first of all, we have to integrate this one. So let's write this one as integral 1 over x ln x square plus 4. Okay, so how can we integrate this one? If you look at the denominator, we have ln and we have 1 over x. So we have the derivative outside. So we can go ahead and use the u substitution. So if we pick u as ln x, u is equal to ln x, we know that du is going to be 1 over x dx, right? And that's what we have. Now we can go ahead and write everything in terms of u. So if we write everything in terms of u, this is going to be just u. So 1 over x dx is equal to du, and ln x is equal to u. So we can write this one as 1 over u square plus 4, right? And if you do the integration for this one, that's going to give you half tan inverse u by 2, right? So now we can bring back this value ln x and plug in terms of u. So this is going to give us half tan inverse ln x by 2, right? So now what you have to do, we have to put the limits of integral. We know that it's going from 2 to infinity, and since this is an improper integral, when we take the limit, we can write this one as half limit t approaches infinity. Then instead of infinity, I plug the t values and calculate this one. So here, what I'm going to write is tan inverse, and we got ln x over 2, right? Tan inverse ln x over 2. So instead of saying 2 to infinity, I say 2 to t, and then find out the value that gives, right? 2 to t. So if we expand this one, that's going to give us half limit t approaches infinity, and if we expand this one, this is going to be t. First we plug the t, so this is going to be tan inverse ln t over 2 minus tan inverse ln 2 over 2, right? So this is what we are going to have. Now we have to know what happened. Now when we do the limits, we are going to plug the infinity for the t value, right? So when we plug the infinity, we know that it's going to be tan inverse infinity. So when it's become tan inverse infinity, what's our value is going to be? So let's look at the graph. So if we draw the graph for tan inverse graph, it's going to look like this. So here we are going to have this one. So as you know, so the graph is going to be like this, right? As the tan goes to infinity, that reaches pi by 2, and here as tan reaches negative infinity, this reaches negative pi by 2. So here we are having positive infinity. So this is going to reach us 5 by 2, right? So if this is reaching 5 by 2, then 5 by 2 minus this value, this is a finite number. And if you subtract this one by a finite number, you're going to get an answer, a finite number, right? So we have a finite number. So if we get a finite number that converges, so if the limit converges, then we can, if the integral converges, then we can go ahead and say, therefore this series also converges. Therefore that's how we determine whether the series converges or diverges using integral test. I hope you guys found this video helpful. See you next time.